You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The purpose of Domain 1 is to establish the conceptual foundation for cloud security. Before discussing operations, governance, or compliance, you need a solid grasp of what cloud is, how it is structured, and how design decisions create both opportunity and risk. This domain frames the models, roles, and architectural choices that underpin everything else. Think of it as the blueprint. Without it, controls may be misplaced or incomplete. For CCSP learners, Domain 1 provides the base vocabulary and reasoning patterns that inform every other domain. In practice, understanding these concepts enables professionals to evaluate architectures, align responsibilities, and design solutions that balance scalability, efficiency, and security. It is the why and how behind every cloud control that follows. The scope of Domain 1 is broad, covering cloud characteristics, service models, deployment models, roles, and architectural patterns. It introduces the essential traits that define cloud computing and establishes how responsibility is distributed. It also explains the ecosystem of participants, providers, consumers, auditors, brokers, and carriers, each with defined functions. Reference architectures provide standardized approaches that ensure solutions are both repeatable and auditable. Together, these elements allow you to move from abstract concepts to structured reasoning. For exam purposes, questions about scope test whether you can locate concepts correctly within the cloud framework. In professional practice, scope prevents gaps by ensuring you know who does what and how patterns should be applied. Core characteristics of cloud computing, as defined by NIST, are on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. On-demand self-service enables users to provision resources without provider intervention. Broad network access ensures services are available through standard mechanisms. Resource pooling delivers efficiency through multi-tenancy. Rapid elasticity allows near-instant scaling. And measured service introduces transparency through metering. These characteristics define cloud's DNA. For exam purposes, recognizing them ensures you can distinguish true cloud from adjacent concepts like virtualization. For professionals, they highlight both benefits and challenges. Flexibility and agility are balanced against governance and control requirements. Service models, infrastructure as a service, platform as a service, and software as a service define, where the boundary of responsibility lies between provider and consumer. In IaaS, consumers control operating systems and applications. In PaaS, they focus on code while the provider manages infrastructure. In SaaS, they simply configure and consume applications. These models shift the shared responsibility line upward as you move from infrastructure to software. For CCSP candidates, exam questions often hinge on identifying which responsibilities remain with the consumer. In practice, this understanding ensures clarity when negotiating contracts, configuring controls, or assigning accountability. Deployment models public, private, community, and hybrid describe ownership and integration. Public cloud is multi-tenant, owned by providers, and available to the public. Private cloud is dedicated to a single organization, offering more control at higher cost. Community cloud supports a group of organizations with shared needs, balancing efficiency with governance complexity. Hybrid cloud integrates two or more models, demanding strong interoperability and consistent controls. For exam readiness, deployment models often frame scenario questions about compliance, performance, or integration. In professional contexts, they guide decision-making, ensuring architectures align with organizational goals and constraints. The cloud ecosystem introduces 5 roles: provider, consumer, auditor, broker, and carrier. The provider delivers services. The consumer uses them. The auditor ensures compliance and trust. The broker manages and integrates services on behalf of consumers. And the carrier provides the network connectivity enabling access. This model clarifies responsibilities across stakeholders, reducing confusion in accountability. For CCSP study, recognizing roles helps parse exam scenarios where multiple parties interact. In practice, this model ensures contracts, audits, and governance align with real-world responsibilities. Reference architecture patterns are standardized templates for building cloud systems securely. They provide tested combinations of services, controls, and workflows that solve common problems. By relying on reference architectures, organizations avoid reinventing the wheel and gain assurance from established practices. For the CCSP, reference patterns demonstrate how principles translate into real designs. In professional life, they save time, reduce risk, and provide audit-ready blueprints for recurring challenges. Multi-tenancy and isolation are non-negotiable design constraints in cloud. Multiple consumers share infrastructure, but each must be isolated so data and processes remain secure. This isolation is achieved through virtualization, container boundaries, and network segmentation. The risk of noisy neighbors or side-channel attacks highlights why strong isolation matters. For CCSP learners, exam items often test whether you recognize multi-tenancy as both an advantage and a challenge. In practice, it drives the need for verification through monitoring, testing, and independent audit. Virtualization mechanisms and hypervisor types directly influence isolation, performance, and attack surface. Type 1 hypervisors run directly on hardware, offering strong performance and isolation, while Type 2 hypervisors run on host operating systems, introducing more overhead and potential risk. Vulnerabilities like hypervisor escape illustrate how core infrastructure security cascades into tenant risk. For exam preparation, understanding hypervisors grounds your knowledge of IaaS. For professionals, it informs patching priorities, monitoring strategies, and contractual questions about provider controls. Containerization packages applications with their dependencies, offering lightweight isolation compared to virtual machines. Orchestration systems, such as Kubernetes, manage scaling, deployment, and resilience across clusters of containers. Containers support cloud-native architectures, microservices, and rapid elasticity, but they also introduce risks such as misconfiguration or container escape. For CCSP learners, containerization terms highlight modern architectures where portability and speed meet governance and control requirements. Serverless computing pushes abstraction further, enabling event-driven execution where the provider manages infrastructure completely. Consumers deploy functions that run in response to triggers, with billing tied to execution. This model shifts operational responsibility dramatically, reducing consumer burden but also reducing visibility. Security for serverless emphasizes code quality, access control, and monitoring of event flows. For CCSP purposes, serverless scenarios underscore the changing lines of shared responsibility and the need to adapt controls to high-abstraction platforms. Data architecture considerations address how storage is designed, how consistency is managed, and how data is placed geographically. Choices about storage models object, block, or file intersect with performance, cost, and compliance. Consistency models strong versus eventual effect application behavior. Placement strategies consider data residency, sovereignty, and redundancy. For the exam, these terms test whether you can connect architecture to compliance and performance requirements. In professional practice, they shape resilience, efficiency, and regulatory alignment. Network architecture considerations highlight constructs like virtual private clouds, subnet segmentation, and layered defenses. Designing isolated subnets for public-facing and private workloads enforces defense in depth. Network segmentation restricts lateral movement, while VPCs provide logical separation within provider infrastructure. For CCSP learners, these terms reinforce that cloud networking retains traditional security principles while adapting them to virtualized contexts. Identity and access architecture is central to secure cloud design. Federation enables trust between identity systems, single sign-on reduces password fatigue and centralizes control, and centralized authorization enforces consistent policies. These constructs reflect identity as the true perimeter in cloud environments. For exam preparation, identity architecture terms appear repeatedly, since access mismanagement remains a leading cause of breaches. Trust boundaries and threat modeling round out the design framework. A trust boundary marks where data or control transitions between actors, such as from consumer to provider. Threat modeling then identifies risks at these boundaries, guiding control selection. Together, they ensure designs are proactive, anticipating threats rather than reacting. For the CCSP, questions about trust boundaries test whether you can spot where controls are needed most. Secure by design principles anchor all architecture decisions. Least privilege ensures minimal access, defense in depth layers protections, and secure defaults reduce reliance on user choices. These principles shift the mindset from patching vulnerabilities to preventing them through design. For exam purposes, they illustrate the philosophy behind correct answers. In practice, they distinguish mature architectures from ad hoc deployments. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Resilience patterns ensure that cloud systems can continue functioning even when components fail. Redundancy provides duplicate systems so that if one fails, another takes over seamlessly. Failover is the automatic switch from a failed component to a healthy one, ensuring continuity without manual intervention. Graceful degradation allows systems to continue offering reduced functionality instead of failing completely under strain. These patterns illustrate the philosophy that failure is inevitable, but disruption can be minimized. For the CCSP, resilience patterns emphasize that secure design is not only about protecting against attacks, but also about maintaining availability under unpredictable conditions. Availability and disaster recovery objectives use Recovery Time Objective, RTO, and Recovery Point Objective, RPO, to guide planning. RTO defines how quickly a system must be restored after disruption, while RPO defines how much data loss, measured in time, is acceptable. Together, they translate business priorities into technical requirements. For example, an RTO of 1 hour and an RPO of 15 minutes demand both rapid failover and frequent replication. On the exam, these terms appear in scenarios linking resilience planning to risk management. In practice, they align investments in redundancy and backup with organizational tolerance for disruption. Scalability patterns emphasize the ability to grow or shrink resources in response to demand. Horizontal scaling adds instances such as more virtual machines or containers, while vertical scaling increases capacity of a single instance. Automated elasticity makes scaling dynamic, responding to metrics like CPU load or request volume. This capability supports both cost efficiency and resilience, since resources adjust to actual demand. For the exam, scalability concepts highlight the difference between architectures that can flex and those that bottleneck. In the real world, scalable designs ensure that applications remain available and performant under variable workloads. Performance and capacity planning require anticipating how workloads will behave under different conditions. Metrics like latency, throughput, and concurrency guide decisions about instance types, storage options, and network design. Forecasting demand prevents both under-provisioning, which causes outages, and over-provisioning, which wastes resources. In cloud, capacity planning is both technical and financial. Performance decisions directly affect cost. For CCSP learners, exam questions on performance and capacity planning emphasize balancing efficiency with resilience, ensuring systems deliver required service levels without unnecessary expense. Observability architecture provides the visibility necessary for detection and recovery. It includes metrics for quantitative monitoring, logs for detailed event recording, and traces for mapping transactions across distributed systems. Together, these provide a holistic view of both control plane and data plane activity. For exam purposes, observability terms highlight the role of visibility in governance and operations. In practice, observability ensures that when issues occur, whether failures or attacks. Professionals can diagnose, respond, and improve systems based on evidence. Without observability, resilience and security remain guesswork. Encryption architecture secures data in its three states: at rest, in transit, and in use. At rest, encryption protects stored data against unauthorized access. In transit, it secures data moving across networks. In use, advanced techniques such as homomorphic encryption or trusted execution environments protect data while being processed. For CCSP learners, exam items often test recognition of these states and their corresponding controls. In practice, encryption architecture ensures comprehensive coverage, preventing blind spots where data is exposed. Key management architecture underpins encryption. Key management services, or KMS, automate lifecycle tasks like creation, rotation, and revocation. Hardware security modules, or HSMs, provide tamper-resistant storage for high-assurance environments. Bring Your Own Key, or BYOK, allows customers to import their own keys into provider systems, while Hold Your Own Key, or HYOK, keeps keys entirely outside provider control. These options reflect varying needs for control, assurance, and compliance. For CCSP candidates, questions on key management often hinge on recognizing which model aligns with organizational governance requirements. Governance architecture applies automation to enforce policies. Policy as code encodes requirements into machine-readable rules, guardrails block unsafe configurations before deployment, and exception workflows handle cases where deviations are justified. These mechanisms scale governance across large, dynamic environments. Exam items referencing governance architecture often highlight how automation ensures compliance without slowing agility. In practice, governance architecture balances innovation with accountability, ensuring cloud use remains aligned with organizational policies and external regulations. Compliance alignment maps cloud controls to established frameworks. Standards from the International Organization for Standardization (ISO), or reports like System and Organization Controls (SOC), provide benchmarks for assurance. Mapping controls ensures that architectures meet both internal and external expectations, enabling audits and certifications. For CCSP learners, compliance alignment concepts reinforce that security is not only technical but also regulatory, ensuring trust with stakeholders. Zero Trust architecture applies an assume breach model to access decisions. Instead of granting trust based on network location, Zero Trust requires verification for every request, regardless of source. In cloud, this model is particularly relevant since perimeters are porous. Zero Trust emphasizes identity, strong authentication, continuous validation, and context-aware policies. For the exam, ZTA references test whether you can connect modern access principles with cloud realities. Edge and hybrid integration patterns address the complexity of connecting systems across environments. Edge computing processes data close to where it is generated, reducing latency, while hybrid integration links cloud with on-premises systems. These patterns raise challenges around consistency, data movement, and governance. For CCSP learners, recognizing integration patterns ensures you can design secure and efficient architectures across diverse environments. Cost-aware design reminds professionals that security must balance protection with efficiency. Right-sizing, scaling policies, and economic trade-offs influence design decisions. For example, replicating data across regions improves resilience but increases cost. Exam scenarios often test whether you recognize that secure design includes financial stewardship, ensuring solutions remain sustainable. Vendor lock-in is a risk when architectures rely heavily on proprietary services. Strategies to mitigate lock-in include modular design, use of open standards, and portability across providers. On the exam, recognizing lock-in risks signals maturity in architectural reasoning. In practice, avoiding lock-in preserves flexibility and bargaining power, ensuring long-term resilience. Design documentation supports auditability and communication. Documenting architectures, decisions, and controls provides evidence for assurance and clarity for stakeholders. It ensures that security is not only implemented but also explainable. Exam references to documentation emphasize its role in governance. In professional contexts, it anchors collaboration across technical, compliance, and business teams. Domain 1's relevance to the exam is profound. It serves as the conceptual base that informs decisions in all other domains. From identity to compliance, every area builds on the models, patterns, and principles outlined here. For professionals, mastering Domain 1 provides the lens through which all other security concerns are evaluated. In summary, Domain 1 establishes the principles, models, and patterns that guide secure cloud architecture and design. It explains how cloud is defined, how it is delivered, and how it must be governed. From service models to trust boundaries, from resilience patterns to governance automation, this domain lays the foundation for all cloud security reasoning. For CCSP learners, it is not only a section of the exam, but the framework that makes sense of every other domain. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.